Hey there, in this video we're going to go over section 7.2, which is confidence intervals for a single mean. Last time we talked about finding the confidence intervals, or in the previous video for section 7.1, finding confidence intervals for a population proportion. So now in section 7.2 we move on to finding the confidence interval for a population mean. So last time we did a confidence interval is found by using the statistic or the point estimate plus or minus your margin of error. So a statistic plus the multiplier times the standard deviation of our statistics. So for the section 7.1, our point estimate was our p hat, the sample proportion, plus or minus our critical value. This is the multiplier times the standard deviation of our sampling distribution. So it's the square root of p hat times q hat over n. In this section, we're going to talk about the confidence interval for a population mean. And so when we have large samples and we can assume a normal shape distribution, there are shortcuts that we can apply to find this confidence interval. So we're going to still use the statistic plus or minus a multiplier, the z-score multiplier times the error when we know the population standard deviation. So remember, sigma is the symbol for population standard deviation. And we're going to use the statistic plus or minus a t critical value from a t table that we're going to talk about times the error when we don't know the population standard deviation. So this is a pretty big deal. So when we know the standard deviation of the population, then we use the z-scores as we did for proportions. We're going to be looking at the z-scores table. But when we don't know sigma, or we have a small sample, so less than 30, we're going to use a t-distribution. Just to remind ourselves, the central limit theorem for the sample means was that if you have samples that are greater than 30 or your sample comes from a population that is already approximately normal, then the standard deviation is equal to the population standard deviation divided by the square root of n. And the means are the same. The mean of the sampling distributions is the same as the population mean. And if we don't know, so let me highlight that, when we don't know the value of the population standard deviation, then we use the approximate, the sample standard deviation as divided by the square root of n. So let's try this example of sleepless nights. And this is an example when the population standard deviation, so sigma, is not known. So my question is, how much do ARC students sleep on a typical night? And let's make it more specific and ask about the previous night. So I assigned a survey and asked you to take it, and so that was about the prior night. Is the average less than the recommended 8 hours? So it is recommended that people sleep 8 hours in a night, so I wanted to see how much do ARC students sleep on a typical night. So what is the, describe in words the relevant parameter of interest in the study, and what symbol would you use? And so looking back at the example, notice that it says, is the average less than the recommended 8 hours? So we are looking at the average. So that is going to be our parameter. So what symbol do we use for average? So we're going to say that the parameter is the average number of hours slept on a typical night. And because we're dealing with a population parameter, our symbol is going to be the Greek letter mu. So mu is the average number of hours slept on a typical night, and we can be a little more specific and say by ARC students. So that is our parameter. So let's investigate whether the mean amount of sleep last night for the population of all students at American River College, your school, was less than 8 hours. So this is going to come in handy for our hypotheses. So we want to investigate whether ARC students sleep on average less than 8 hours. And we're going to assume that the population is normally distributed. So this is mainly here so that we can use the central limit theorem later. depending on the size of our sample. Because if our sample is smaller than 30, we may not be able to use the central limit theorem. So this says, well, assume our population is normally distributed. So it's guaranteeing that we can use the central limit theorem. Now, express the null and alternative hypotheses for investigating this question. Use words and symbols. So we want to investigate whether the mean amount of sleep is less than 8 hours. So the null hypothesis is usually the standard, right? The claim. So the standard is the recommendation is that people sleep on average 8 hours. So that's going to be our null hypothesis. So in words, we can say the average number of hours slept on a typical night is 8 hours. And then in symbols, we can say the parameter mu is equal to 8. And the alternative hypothesis is usually the question, what are we looking at? What do we want to investigate, right? The conjecture. So we want to investigate whether the mean amount of sleep, let me highlight that real quick, is less than 8 hours. So that's what we want to investigate. So that's going to be our alternative hypothesis. So in words, we can say the average number of hours slept on a typical night is less than 8 hours. And in symbols, we're going to say H sub A, right, for alternative. The 0 is H null, or the null hypothesis, and HA is the alternative hypothesis. So the average, the mean number of hours slept the previous night is less than 8. So ideally, how would you obtain a sample from the population of all students at your school? So what will be the ideal situation? Ideally, for any study, we want to make sure that we have a simple random sample. So that will be the ideal. We want to obtain a simple random sample. And so we will say go to random places at the college, right, to survey students from the population. So the student union, the sporting event, or tutoring center, random ARC classes, not even necessarily classes that you're taking, but just you want to get a really random sample of all ARC students. So you would go to places that are not necessarily convenient to you. What variable would you measure on each student? We will measure the number of hours that they slept last night. So while obtaining a simple random sample of students from ARC is an ideal way to attempt to get a representative sample, there is no question that it will take a lot of time, effort, and energy for you to make that happen. Sometimes we have no choice but to rely on a convenient sample instead. Right? Look above at part D. So to get a simple random sample, some of the ways that I listed is go to random places at the college to survey students, the student union, sporting event. So in order for you to go to all those places, go to a sporting event, go to a tutoring center, maybe like find the times that the tutoring center is the busiest, go to random ARC classes. So that takes a lot of time, effort, planning. And so some people may not be up for the challenge. And so a convenient sample is used instead. So like me, in this case, I'm going to use this class as our convenient sample. So that's why you guys filled out the survey. How many hours did you sleep last night? So that was a very convenient sample for me, even though it is still, you are ARC students, so it is a sample of ARC students, but it's a very convenient sample, right? So we will revisit the implications of using this class as a sample of ARC students later when we evaluate our study. For now, let's gather the data. So you already took the sleep survey, and I have uploaded the data to StatCrunch. So if you want to pause the video and you can go to StatCrunch and take a look at the data. But I'm gonna move on to part G. Identify at least one way that your class is likely a good representation of all students at ARC in terms of hours slept last night. Well, and I already mentioned one of the reasons that you are a nice convenient sample is, well, you are ARC students. So you are part of the population. So that one works. Any other reasons? I'll look forward to seeing your notes and see what other reasons you put in there. And I'll try to then put some of those reasons back in this notes. Identify at least one way that your class is likely not a good representation of all students at your school in terms of hours slept last night. So what is at least one way that this class is not a good representation of all ARC students? So pause the video, kind of think about it, and then make sure you add that in your notes for submission at the end of the week. Some of the things that come to mind is that this is an online class instead of an in-person class, right? Like if someone's taking a STATS 300 class in person at say 9 a.m., that may affect what their hours of sleep the previous night. What else? Maybe the reason you're taking this class online is because you work full time. So varying schedules. And so if you work full time and then you're taking this class, that may affect the hours of sleep that you get at night. And so there could be various things, right? This isn't a representative of all ARC students. So there are some drawbacks to having a convenient sample like this. All right, so let's use the data from your class in StatCrunch to find the following summary statistics. So go on to StatCrunch and let's find the sample size, sample mean, and the sample standard deviation. So you can access StatCrunch from your textbook, or I also put it in that module with statistical technology, so you can access it from there. And so what we're going to do is we're going to go over, I know it's off the screen here, but there's my StatCrunch. So when you go to my StatCrunch, go to my groups, and then choose the Stat 300 Fall 22 group. And we're looking for sleep survey results. So here we go. So here is our data. I did combine your data with my, so the two stat classes, I combined them just so that we made the sample a little bit bigger. So this is the hour, these are the hours slept last night. So let's go to, how do I find the mean and standard deviation in the size of the sample? So with StatCrunch, we go to Stat, Summary Stats, Columns. And so once you have columns, you want to choose the one. So hours of sleep, then we want to pick N, control, mean, and then press control and hold it down and standard deviation. So there's N, mean, and standard deviation. So N, the size of the sample. So compute, and it gives us our result. So there are 39 total that took the survey. The mean is 7.37 and the standard deviation is 1.5. So under 8 hours already the mean and the standard deviation is 1.5. So okay, so that puts us, and you can kind of see based on the data here, there are some that are 10 hours of sleep, 9 hours of sleep, but then there's one that is 3.75 hours of sleep. So it's interesting then to see, do we have any outliers? How do you quickly check if there are any outliers without having to look at the data? And even then, right, like, is that really an outlier? A quick way to check is to graph a box plot and choose the column for hours of sleep. With box plots, make sure that you draw boxes horizontally. And then let's mark the mean just to see where it is and compute. And so here's our box plot. So actually 3.75 does not appear to be an outlier. If we had outliers, right, they will be on the size of the fences. You would have a dot over here. So for example, if I add in, say, what would be a good outlier, say 16. Hopefully nobody's sleeping 16 hours. But just to see, let's go to edit and let's keep it and compute again. So now notice that it gives me an outlier. So that 16 is very far away from the mean, more than 2 or 3 standard deviations away. So, but that 3.75, even though it kind of looks like it might be an outlier, it turns out that it's not. Right? Because it doesn't show us a dot over here unless I'm missing it. Okay. So, but this is where our data is. Notice our mean is to the left of the median, so this graph will be slightly skewed left. So I am going to copy this results and bring them back to our notes. Now that we're back at our notes, here's our summary statistics. So N is 39. The mean, let's round to 3 decimal places. So let's say 7.372. And the sample standard deviation also, let's round to 3 decimal places. So 1.521, rounding to 3 decimal places. All right, so now based on our sample data, what is your best guess or estimate for the value of mu, the parameter? So the average number of hours slept by ARC students the previous night. And how could you check to see if your estimated value is indeed a plausible value for mu? So we can say, well, let's see, the average is 7.37. So what would you say? It does appear to be around 8, right? So we can say that parameter looks like it is 8. So let's just say it appears to be close to 8. Now, how could you check to see if your estimated value is indeed a plausible value of mu? We could run a simulation, and remember with the central limit theorem, right, it tells us that the more samples that we take, and if it's normally distributed or more than 30, the mean of the sampling distribution is the mean of the population. So we could do a simulation and see if we have a sampling distribution, then our mean of the sampling distribution is the same as the mean of the population, but we can use the central limit theorem to accomplish the same thing. So we can say, well, because our sample was 39, so bigger than 30, we can say that the mean of the samples is close to the mean of the population, so we can say it is 8. All right, so let's do the confidence interval now for the population mean. And this is again, with sigma not known, because that's what we're doing. So we don't know sigma in this case, the population standard deviation. Just as we did before, we need the margin of error. And so the error is going to be the critical value, in which now we're going to look at the t-table times s over the square root of n, using degrees of freedom n minus 1. So I'll talk about what that means. Here, because we are greater than 30 and the population is normally distributed, but we're using the t critical value because we don't know sigma. And so, but from the central limit theorem, we can use the standard deviation, we can approximate it using s divided by the square root of n. So I'll just bring you back to that summary of the central limit theorem, right? So if our sample comes from an approximately normal distribution, then the mean is equal to mu, and the standard deviation is equal to s over the square root of n when we don't know the population standard deviation. So this is what we're using, s over the square root of n for the standard deviation. So going back over here, that's what we have here, using degrees of freedom, n minus 1. And so the degrees of freedom, what this means is because we are taking samples from the population, and so to kind of adjust for the difference from sample to sample, then we adjust by one element. So if our sample has 39, so I'm going to account for 38 data values. If my sample had 41, I would account for 40 data values. So this is just for kind of almost like throwing out one data point just to adjust for variability. So that's what's going on here. And then the confidence interval is then your point estimate, which is x bar, plus or minus the error. And so the error formula is given up here. And this is what's called, so the t is called the student t distribution. So if a population has a normal distribution, then the distribution of t, notice that it looks just like a z-score, right? Our X bar from the sampling distribution minus the mean divided by the standard deviation, but we use the central limit theorem, standard deviation. We don't really call it the student t distribution, we just call it a t distribution. And X bar is the point estimate. Does our sample meet the requirements to approximate the population mean? Yes, right, it does meet the requirements. We were told that it was approximately normal, but also we have that our n is greater than 30. Our sample size is 39, so it definitely meets the requirements. And will we use z alpha over 2 or t alpha over 2? I kind of gave it away when I said t alpha over 2, but how do you know? We don't know the population standard deviation. So it's a big deal. Like if you know it, then you use the z-scores. If you don't know it, then you use the t-scores. So we are going to use t alpha over 2. That is our critical value. So I wrote in here the explanation why does our sample meet the requirements? Our sample is larger than 30, but it also comes from a population that is normally distributed. And we will use the T alpha over 2. Why do we use that? Because we don't know sigma. The population standard deviation. So now part L, calculate or approximate the standard deviation for the sampling distribution of our means. So we're going to use the formula from the central limit theorem, which is in this box over here. Because we don't know sigma, then we're going to use this as the standard deviation, so S over root n. So we need to find S over the square root of n. So from the work that we did in StatCrunch, we know that the sample size was 39, or mean 7.372, and our standard deviation was 1.521, the sample standard deviation. So that means this is going to become then 1.521 S over the square root of n, and n is 39. And so let's put that on our calculator and see what we get. And when I put in my scientific calculator, I got 0.24355. So I'm going to go a little bit longer with this, more decimal places, just because otherwise I might lose some significant digits in approximating. So when we go find the critical, the standard error E, I might actually just leave it as 1.521 over the square root of 39, or add more digits, right? So how many do I have? 1, 2, 3, 4, 5 decimal places. 4 to 6 will be good, so I'm gonna just leave it at 5. Okay, so now we have our standard deviation that we can use, and now we're gonna, in order to calculate the standard error, we first need to find the required critical value to determine a 95% confidence interval for the population. So we need to find the required critical value, which is a t sub alpha over 2. So how do we find that? All right, so we're going to still find the same way that we did for a proportion. We need to find the critical value, so we need to figure out alpha and our alpha over 2, right? We need t sub alpha over 2. So when you have a 95% confidence interval, what's alpha? And then also what's alpha over 2? So let me go to my notebook over here. So the required value of alpha will be, how do we find it? We usually do, so 95% confidence means that alpha is 1 minus 0.95, right? So 95% as a decimal is 0.95. So then alpha over 2 will be, this is 0.05. And then alpha over 2 then is 0.05 divided by 2, which is 0.025. So that's our alpha over 2. So now we go into our textbook to find the t-table. So when you're in your textbook, let's go to the table of contents. And then we're going to go all the way to the bottom to z-scores and t-values. And close that one out. There's our z-scores, the negative z-scores, positive z-scores. And if you keep going, then there's your t-distribution for critical t-values. So this is what we want. Now our degrees of freedom are the size of our sample, right, n minus 1. So we kind of think of it as throwing one value out just to accommodate for variability from sample to sample. So our sample was size 39, so then we're going to go to 38. So that's what I'll be looking for, and I want 95% confidence, so that means our alpha was 0.025. So here is area in one tail. So we're going to be looking at area in one tail, 0.025, or you can look at area in two tails, which is 0.05. So notice that these line up. And so the reason for that is going back over here, right? When you have a t-table, or when you have, sorry, the bell curve, right? And then you go, okay, here is 95%. Then the two tails have the rest, the other 5%. So then when you're looking at the two tails together, they make 0.05, right? This 0.05, but when you look at just one tail, then it's half of that. So this is 0.025. So that's why it says either look at one tail and that will be 0.025, or if you look at the two tail, then you're looking at 0.05 total. And this looks a little weird with that being 0.025. So together is 0.05. So when you're looking at your table, that's what we're looking at. So over here back at our table, right, we're either looking at a one tail to the left, or we're looking at a two tail. And so, but notice that they line up anyway. 0.025 in one tail is the same as 0.05 in two tails. And so we're going to go to 38, which was over here, so 2.024. So 38 and 0.025 for our one tail. So if I had a better way of doing this, then it's this spot over here. So I guess I can highlight it. So 2.024 is our critical value. And I can say then my t sub alpha over 2 is 2.024 from the table, from the t-table. So now that we have that, we can calculate the standard error. And we have said our standard error is the critical value alpha over 2 times the standard deviation of the sampling distribution, so that from the central limit theorem is S or the square root of n. So then this is going to be 2.024, or critical value that we found from the table, times S divided by the square root of n. So the square root of 39, and I need to look up what S was, or S was 1.521. So we're going to put that over here. And then calculate that in your calculator and see what we get. So when I did it in my calculator, I got 0.4295. So let's say 42. Sorry, it was 49. So this will be 0.49 and then 295. So 493. So let's approximate it to that. So that is our error. So now that we have the error, we can continue finding the confidence interval by doing the sample statistic plus or minus the margin of error. So that means that our confidence interval, 95% confidence interval, then is our x bar minus the error and then x bar plus the error. And this is approximating mu. So I should have mu in the middle here, the population parameter. And so now we can say, remember, our sample mean was 7.372. And so minus the error, which is up here, 0.493. So minus 0.493 is going to be smaller than the population parameter, and then that smaller than, again, our mean 7.372 plus the standard error of 0.493. And so when we add those up or compute that, that is giving us essentially with 95% confidence where our parameter is going to land, between what two values can we expect our mu to be. So for the lower limit, I get 6.879, and for the upper limit, I get 7.865. So this is our sample mean plus the standard error, or sample mean minus the standard error. So this gives us an approximation for where the population parameter is. Remember, the population parameter was the average number of hours slept by RC students the previous night. So notice that this entire interval is less than 8. So the upper limit is less than 8 hours. 8 hours is the recommended amount. So when interpreting this confidence interval, we can say, based on this sample, we can, with 95% confidence, say that ARC students appear to sleep less than the recommended 8 hours of sleep per night. So always when you interpret a confidence interval, write it in the context of the problem. So let me just repeat that. And we can say with 95% confidence, the average, right, or parameter, the average number of hours slept by ARC students on a typical night is less than the recommended amount. And that's because our upper limit, well, both the entire interval is under 8 hours. So we can say, well, then the parameter is going to be definitely under 8 hours. So ARC students are sleeping under the recommended amount. So back to the note here, you would interpret the confidence interval, which is what I already said, right? Like, so we can say with 95%, we're 95% confident that the population parameter, so the average number of hours that ARC students sleep on a typical night, is between the lower limit and the upper limit. And we can say that since both of those are under the recommended 8 hours, we can generalize it and say we are confident 95%, we're 95% confident that ARC students sleep on average less than 8 hours. So here, unlike Z-score multipliers, for the confidence intervals for population proportion, there are a lot of t-score multipliers used for confidence intervals for the population mean, and that's because t-score multipliers are based on the sample size. And so to account for the variability between samples, the t-score multiplier is based off of the degrees of freedom, so n-1. So again, think of it as just throwing out one data value to accommodate for the variability in sample size. And essentially, when you look at the T-table, see if I still have it up. So notice that it still looks pretty bell-shaped, and your textbook actually has a pretty good image of when the sample size, as the sample size changes. So what happens is, if you notice over here, when you have large sample sizes, notice that these values are already then the Z-scores. For 95%, 1.96 is our usual Z-score multiplier. For a 90% confidence interval, 1.645, and so on. So these, as your samples get larger and larger, the T's distribution becomes the normal distribution. But when you have smaller samples, then the T multiplier is going to change depending on the sample size. So notice that a 95% one-tail confidence interval, the T multiplier, right, is we're looking at alpha over 2 is 0.025, but notice how the values change because it's based on the size of the sample. And so now if you would like to increase your level of confidence to say 99%, all you need is a new t-score multiplier. So everything will be the same except Now the T alpha over 2 is different. So let's calculate that. So try it on your own first. So so for 99% confidence, it will be 0.99. So it'll be 1 minus 0.99 will give you alpha, and then alpha over 2. And then look it up on the t-table. And I'll record another video where we'll finish this and the rest of the examples.